when you throw something like this, and there's no forces acting on it, it moves in a straight line, all that kind of stuff. So he's saying, suppose there exists such a frame. Okay, we will call, and then we're going to do all kinds of stuff with that frame, but suppose there exists such a frame. Let's call that frame the stationary frame. And then he states his principle, the principle of the constancy of the velocity of light, which reads, any ray of light moves in the stationary system of coordinates with the determined velocity c, whether the ray be emitted by a stationary or by a moving body. Okay, so let me just paraphrase that. So combining what I just said, I'm going to write it this way, and we'll talk about it. Okay, so for an observer at rest, the speed of light is c, independent of the motion of the source. Okay, so that's what Einstein said. So let's have a look at this. So first of all, at rest, for an observer at rest, well, we know that there's no such thing as absolute rest. That's one of the ideas that we can anticipate what's coming. We know there's no such thing as absolute rest. There's no such thing as absolute space and all that. That's what we're going to get to. Okay, so when we say an observer at rest, we put it in quotation marks, indicating that really what we need is what Einstein is saying here. There exists at least one frame of reference in which it is true that Newtonian mechanics holds good. Okay, if I throw an object and there's no forces acting on it, it will move in a straight line. There exists at least one frame in which that's the case. So this is the frame that Einstein calls the stationary frame. Okay, so I'll just say this thing. So there exists at least one frame in which this is true, in which the speed of light is c, independent of the motion of the source. Okay, so at the time, this is 1905, people had in mind that most physicists thought that light is a wave in ether. Okay, so is this principle true for light is a wave in ether? Why? So let's tell me why. Yeah, it's exactly the same as a sound wave in still air. Okay, so sound waves moving around still air. If you're at rest with respect to air, it doesn't matter how the source is moving around. If there's an ambulance coming towards you or moving away from you, the speed of sound will be the same. You will hear a Doppler shift here. When it's coming towards you, the frequency goes up. When it's drifting away from you, the frequency is lower. But the speed of that sound wave is always c with respect to still air. And if you're at rest with respect to that still air, you will always measure that same c. Okay, and if light is a wave in ether, exactly the same thing applies. Okay, so this principle is obviously true if light is a wave in ether. Phenomenon. Okay, so what I want to, okay, I got it. Okay, so let's just leave it at that. So what I want to emphasize here is that this principle, it would have been completely obvious to anyone in 1905. Okay, there's nothing surprising about it, nothing radical about this principle. Everyone would have read that and said, yeah, okay, that's obvious, so what? Okay, so let me just emphasize, it's very important that we see why it's obvious. Okay, so there's a whole bunch of reasons why it's obvious. One is this. The people at the time had in mind a particular model of light. Okay? They didn't actually know, well, this is what they thought light is. The fact is we still don't know what light is exactly. Okay? We don't, you think about string theory, well, maybe light is these little strings and so on and so forth. Okay? We still don't actually know what light is at a really fundamental level. We understand light a lot better now than we did back then, but we still really don't know what it is. But anyways, so at that time, people had this wave and ether model, this mechanical model of light. That light is this mechanical phenomenon. That's a physical vibration of some medium called the ether. Just like sound is a mechanical phenomenon. It's a vibration of some physical medium. So they have this mechanical wave and ether model. The wave and ether model of light, just like sound and air, predict that this is true. Okay, so everyone would have said, yeah, that's obvious. Way to go, Einstein. The second reason is people were aware also that light is an electromagnetic phenomenon. So Maxwell in the 1860s had come up with Maxwell's equations, which describe how electric and magnetic fields are unified, are just different sides of the same coin, how they work together, how one oscillates and then the other oscillates and so on, how they work together to produce an electromagnetic wave, which moves through space and carries energy and momentum and all that kind of stuff. And it was known that light is an example of an electromagnetic phenomenon. So light is electromagnetic waves of a certain wavelength or a certain frequency range. Okay, so the second thing people would have known at that time is that Maxwell's equations, which describe light, which are the mathematical embodiment of how light behaves, Maxwell's equations also predict this. Okay, so I should elaborate a little bit on that. So what Maxwell's equations say, well, okay, so what Maxwell's equations say is that, at least classically, not quantummechanically, classically, the source of all light is accelerated electric charge. Okay, so what does that mean? So that means if I take a charge like this, a charge at rest will not emit light. A charge in uniform motion will not emit light. But a charge that's accelerated, if I take that charge and wiggle it back and forth, then it will emit electromagnetic waves, which is a form of light. Okay. let me put it this way. Suppose that you are out in space, floating out in space on some platform here, and you see some charge out here, and this charge is moving around in some completely random way, like this. What's going to happen is that charge, which is accelerating, okay, it's changing its velocity, is going to be emitting electromagnetic waves. And those waves will come at you, and independent of the motion of this thing, it's accelerating, it's going to emit electromagnetic waves, and you will see the speed of those waves in c. Okay, if I were to take this same charge, this charge is wiggling around here, and I were to give it an extra drift, okay, to the right, for example, or to the left, okay, so take this whole pattern of jiggling around and add sort of a drift to the right. Okay, well, that's the equation would say it's still just a charge wiggling around, independent of the motion of that source. The speed of the waves you're going to measure is c. Okay, so everyone would look at that and say, okay, yeah, that's right, Albert. And also, there would have been experimental evidence available at this time through astronomical observations. Okay, so it turns out that, so I don't want to get into this, but it turns out that it's very, very simple observations that you can make of binary star systems. So most, the majority of stars in the galaxy are actually binary pairs. So two stars orbiting around each other. There's plenty of examples of this. And if you look with a telescope, you will, and you study the motion of these guys, you will also conclude that the speed of light is independent of the motion of the source. The source in that case being either star. And so at one time the star is moving towards you, and another time it's moving away from you, and so on. Simple observations that I want to get into give you strong experimental evidence that the speed of light is independent of the motion of the source. Okay, so everyone would have believed this. Everyone would have said, yeah, totally obvious. I want you to compare this statement that I wrote down here with a seemingly, with a closely related statement, but a totally different statement, and that is, that's called a T2 prime. Okay, so this is what Einstein did not say.